So in the previous video, we started to study limits, but not limits in the way we saw them earlier in the class when we were talking about removable discontinuities, but instead limits that somehow involve infinity. Really, we're interested in two different cases. Limits where there's an infinity symbol somewhere kind of in the question, and limits where the answer ends up being equal to infinity. In this video, we're going to study the first type, the type when you have limits with infinities in the question. We saw several examples of that in the last video, and a lot of that knowledge will come into play in this video, but hopefully it'll be a little bit less theoretical than last time as we deal with more concrete examples. Suppose you were asked to evaluate the limit as x approaches infinity of 6x cubed minus 5x squared plus 7x plus 11 divided by 2x cubed plus x. The first comment that I want to make is this question about what the limit as x approaches infinity of something is equal to is a question you saw in a pre-calculus class. It's really just asking you about the end behavior. And since you probably learned end behavior for rational functions in a pre-calculus class, you might already know the answer to this question. Maybe you learned that in the case where the degree of the numerator, 3 in this case, is the same as the degree of the denominator, 3 in this case, the limit will always just be equal to the quotient of the leading coefficients. In other words, this 6 divided by this 2. You may have learned in a pre-calculus class that if y is equal to 6x cubed minus 5x squared plus 7x plus 11, all divided by 2x cubed plus x, then we can state the end behavior by saying as x approaches negative infinity, the y coordinate is going to approach 3, and as x approaches positive infinity, the y coordinate is going to approach 3. In other words, we have a horizontal asymptote at y equals 3. This is all stuff you were supposed to have learned in a pre-calculus class. And this isn't wrong at all. This is the correct answer, 3. This limit is going to end up being equal to 3. But in calculus, it'll end up being really beneficial to understand why that's the case. Not just coming up with this 3, but understanding why that 3 is consistent with our ideas of limits, and specifically our limit laws. So for our purposes, the way we want to evaluate this limit is we want to take advantage of the fact that you can always multiply the top and the bottom of a fraction by any non-zero number that you want, and as long as you're doing the same number on the top and the bottom, you're essentially just multiplying that fraction by 1, and therefore you're not changing the value of the fraction unless you're not changing this limit. So if I wanted to multiply the top here by 2 and the bottom by 2, that would be totally fine. I don't want to multiply the top and the bottom by 2. What I want to multiply the top and the bottom by is 1 divided by x cubed. Why do I want to multiply the top and the bottom by 1 divided by x cubed? Because of this x cubed in the denominator. Turns out there's an x cubed in the numerator also, but I'm not focused on that one. Because the degree of the polynomial on the bottom is 3, the largest exponent down on the bottom, I want to multiply the top and the bottom by 1 over x cubed. In other words, I want to divide the top and bottom by x cubed. If I divide the top by x cubed, I'm dividing each of these 4 different terms by x cubed. So I would get 6x cubed divided by x cubed. In other words, 6 minus 5x squared divided by x cubed. In other words, 5 over x plus 7x divided by x cubed. In other words, 7 over x squared plus 11 over x cubed. Down on the bottom, I would have 2x cubed divided by x cubed. In other words, 2. Plus x divided by x cubed, in other words, 1 over x squared. Because, informally speaking, I'm doing the same thing to the top and the bottom here, dividing by x cubed, this limit's going to be equal to this limit. But this limit is better in some sense than this limit up here. And the reason why is because my limit laws allow me to take the limit of each of these terms individually. So limit laws is something we talked about several months ago. And I kind of describe them as the reason you're allowed to do the things that you probably think you're allowed to do anyways when you're evaluating limits. You probably think that the limit as x approaches infinity of something divided by something is the limit as x approaches infinity of the top divided by the limit as x approaches infinity of the bottom. And in fact, that is true, as long as the limit on the bottom is not equal to 0. So really, this one question about limits I can think of as 2 different questions about limits. The limit as x approaches infinity of 6 minus 5 over x plus 7 over x squared plus 11 over x cubed divided by the limit as x approaches infinity of 2 plus 1 over x squared. This probably seems like it should be equal to this, but really the reason we're allowed to do this is the limit laws. And the limit laws don't stop there. If you consider the numerator of this fraction, the limit as x approaches infinity of this sum, You probably think you could just take the limit of each of the four terms individually, and in fact, you can, again, owing to the limit laws. This is going to be the limit as x approaches infinity of 6, which is just equal to 6 because there's no x's here, minus the limit as x approaches infinity of 5 divided by x, which maybe you can talk yourself into being equal to 0. Wait, why is the limit as x approaches infinity of 5 over x equal to 0? Well, remember, in the previous video, we showed that the limit as x approaches infinity of 1 over x is equal to 0. Because if I go way to the right on this graph, my height approaches 0. So the limit as x approaches infinity of 5 over x is just going to be 5 times the limit as x approaches infinity of 1 over x. Again, there's a limit law hidden in there. So it's going to be 5 times 0, in other words, 0. Same thing happens with the limit as x approaches infinity of 7 over x squared. That's equal to 0 as well. You could probably talk yourself into that going back to the previous video, or you can kind of just take a more intuitive approach. If x gets really, really large, what happens to 7 over x squared? Well, the top stays the same, it's always 7, but the bottom gets really, really large. A large number squared is even larger. So a number that stays the same like 7 divided by some number that gets arbitrarily large is going to produce an expression that gets arbitrarily small. Try taking 7 and dividing it by, I don't know, 9999999 on your calculator. What you'll end up with is a number really, really close to 0. Same idea for 11 over x cubed. The limit as x approaches infinity of this polynomial up here is just equal to 6. And the same logic works in the denominator. The limit as x approaches infinity of 2 is just equal to 2. And the limit as x approaches infinity of 1 over x squared is equal to 0. Taking advantage of my limit laws, I can evaluate this limit as just 6 divided by 2, in other words, 3. The punchline you probably already learned in a pre-calculus class, but understanding why it works, understanding why you can ignore all of the terms other than the terms with the largest degree, and then you can divide the coefficients on those terms with largest degree to evaluate the limit is really the important thing with this example. Let's see if we can do something similar to evaluate the limit as x approaches negative infinity of this expression. This expression looks a lot like the expression we have up here, but you might notice that the polynomial in the numerator is degree 5 now, and the polynomial in the denominator is degree 3. This trick that we did where we multiplied the top and the bottom by 1 over x cubed is going to be very similar to the trick we do down here, but you might be wondering, wait, should I multiply the top and the bottom by 1 over x to the 5th? Or should I multiply the top and the bottom by 1 over x to the 3rd? Am I dividing by x cubed or x to the 5th? It'll turn out that it'll benefit you to divide by the degree of the bottom. I didn't have to make a big deal of it before because the degrees were the same on the top and the bottom, but down here where they're not the same, it's important how you treat these. I'm going to divide everything by x cubed to get the limit as x approaches negative infinity of 6x squared minus 5 divided by x plus 7 divided by x squared plus 11 over x cubed. Make sure you follow where all 4 of these terms come from. I want to divide that by 2x cubed divided by x cubed, in other words 2, plus x divided by x cubed, in other words 1 over x squared. When I consider the limit as x approaches negative infinity of a constant divided by x raised up to some power, for the same reason that the limit as x approaches negative infinity of 1 over x equals 0, the height going to the left gets really close to 0, the value of each of these different terms is going to get really, really close to 0. So this limit is going to be equal to the limit as x approaches negative infinity of 6x squared minus 0 plus 0 plus 0 divided by 2 plus 0. In other words, the limit as x approaches negative infinity of 3x squared. Our limit laws tell us that that's 3 times the limit as x approaches negative infinity of x squared. And in the previous video, we learned that if n is an even number, the limit as x approaches negative infinity of x to the n power is equal to positive infinity. So since 2 is an even power, the limit as x approaches negative infinity of x to the 2 power is positive infinity. I get 3 times infinity, or infinity, for this limit. You may have been able to evaluate this limit by considering end behavior of this rational function and techniques used in a pre-calculus class, but I think what you'll want to do is think about it using the steps that we did here. Let's do one more rational function example and then we'll call this video good. What's the limit as x approaches negative infinity of 6x cubed minus 5x squared plus 7x plus 11 over 2x to the 5th plus x? As you can see, I'm kind of copying and pasting problems, keeping almost everything the same. The big thing that's changing here is now the degree of the denominator is 5. The degree of the numerator is 3, just like it was in this example, but the degree of the denominator is 5. Much like the example we just did, the degrees are different up on the top and the bottom. We're going to do a similar trick where we divide everything on the top by something and everything on the bottom by something, but we again have to be careful of what that something is. We always want to divide the top and the bottom by the degree of the bottom. So in this case, I want to divide everything by x to the 5th power. If I divide all 4 terms up top by x to the 5th, I will get 6 divided by x squared, because 6x cubed divided by x to the 5th, the x cubes cancel out with 3 of the x's in x to the 5th, and leave me with x squared down on the bottom, minus 5 divided by x cubed, plus 7 divided by x to the 4th, plus 11 divided by x to the 5th. Down on the bottom, 2x to the 5th divided by x to the 5th is just equal to 2, and x divided by x to the 5th is the same as 1 over x to the 4th. I can use my limit laws to say that this limit is the same as the limit of the top divided by the limit of the bottom, and the limit of the top is the limit of each of the terms individually, same as the limit in the bottom. Without even writing any more lines, I can evaluate this limit as 0 minus 0 plus 0 plus 0 for these 4 terms up top, divided by 2 plus 0. In other words, 0 divided by 2, in other words, 0. The limit as x approaches negative infinity of this expression is just equal to 0. Oh, right, I kind of remember that from a pre-calculus class. When I had rational functions and the degree of the denominator was bigger than the degree of the numerator, I always had a horizontal asymptote at 0, which meant that as my x-coordinate tended towards negative infinity, my y-coordinate tended towards 0, which is exactly what we're saying with this limit here. There's a few more cases I want to examine of limits where the x-coordinate is approaching infinity or negative infinity, but I think I'm going to save those for the next video.